Thanks for attending my talk. I'm Kaan, and this work was done together with Jana Gitava, who's sitting right there, and also Gustavo Alonso, our supervisor. So I'm going to talk about FPGA-based data partitioning today. So we all know that partitioning data is necessary and expensive. It is a well-studied problem for general purpose processing. For example, I will mention some of the related work here. So Manigault and others have shown in 2002 already that partitioning that produces cache-fitting hash tables leads to the fastest hash join. However, we all know that data sizes keep increasing and cache sizes do not. So higher fan-out and fast partitioning will keep playing an important role on application performance in the future. So for partitioning, also many CPU optimizations have been explored. Some of the most important ones include software write combining within cache size buffers used by Balkesan and others. Then Wassenberg and others proposed using non-temporal writes using vectorized instructions to bypass the cache and write directly into the memory to avoid cache pollution. And of course, we can do multi-core parallelism. We can utilize the whole CPU to do partitioning. So in short, what I mean to say by this is we know how to do partitioning using a modern CPU. And that's why in this work, we are trying to answer this question. Can we perform data partitioning more efficiently using an FPGA? And why an FPGA? Because FPGAs are becoming very widespread. So the recent release of F1 instances by Amazon, and then the Catapult project from Microsoft, and the acquisition of Altera by Intel, all point to a future data center where FPGA is a cornerstone processor. And we need to understand how to use that processor to perform certain types of workloads. But before moving on, let me first try to explain you why would an FPGA be good at partitioning data? All right, so partitioning can be represented as a data flow where three things happen. First, hashing happens to determine where a tuple belongs to, which partition a tuple belongs to. Then the second step, we want to do some write combining. We want to combine the tuples that belong to the same partition to avoid the amount of, to reduce the amount of random accesses we do. Then we do write back where we determine the end address for the combined tuples and we write the tuples back to the memory. Now if you imagine partitioning as a data flow like this, we have a couple of advantages on the FPGA. The first thing that we can do is we can actually implement arbitrarily complex hash functions on the FPGA without suffering any performance. So the usage, the effects of choosing the right hash function for database operators have been studied by Richter and others in VLDB15. And we, in our own work, have shown that we can implement very complex hash functions like simple tabulation without suffering any performance in FPL16. All right, the second thing is we can also do write combining very efficiently using the large internal buffer space of the FPGA. Which we call block RAMs or BRAMs for short. And these block RAMs provide a very high bandwidth distributed memory on the FPGA logic. Apart from that, we can also use the custom logic capabilities of the FPGA and we can combine all these three stages, we can pipeline all these three stages of the data flow. So imagine when the first tuple is in the write combining stage, the second tuple can already be in the hashing stage, and this can be, these operations can happen in parallel. And last but not least, we can also do scale-out parallelism. So we can instantiate this data flow multiple times if we have enough resources on the FPGA. It is worth mentioning here that the FPGAs at each iteration, each family of FPGAs are becoming larger. So in the future, it will be even easier to use this scale-out parallelism more. All right. So let me introduce you the target platform that we use to test these ideas. And it's actually the platform that David has already presented. It's the Xeon+FPGA. I have just a little bit different representation here, but it's the same thing. So we have a two-socket machine. On the one socket, we have an FPGA, and on the other socket, we have an FPGA. On the one socket, we have a CPU, and on the other, we have an FPGA. And the FPGA can access the main memory using the cache-coherent QPI interface. So any accelerator that we implement on the FPGA can work directly on the main copy of the data. And this architecture is important for us because we would like to perform partitioning on the FPGA, and the resulting partitions should be used later on by a CPU. We would like to perform hybrid operations, and that's why having a shared memory architecture is very important, as I will show you later. However, there are some limitations in this platform, as this is an experimental platform, such as the memory bandwidth, which is around 6.5 gigabytes per second, and also the cache coherence protocol had caused some problems. I will explain more in the evaluation, and I will explain why this is a limitation currently. All right, so specifically what we want to do is we would like to perform a hybrid hash join, hybrid partitioned hash join. So the partitioning should happen on the FPGA, and the build and probe stage of the join should happen on the CPU. And in the end, we would like to evaluate the performance of this and to see if this type of hybrid execution is really efficient or not. So to clarify how the hybrid execution works, let me walk you through a high-level diagram here. We have again the FPGA and the CPU, and we have the main memory where we have the tables R and S. So first we pass the pointers to the FPGA. Then the FPGA reads the tables and produces the partitioned R and S along with the histograms that contains the counts for each partition. And then the multi-core CPU can do build and probe in a shared nothing fashion using the 10 cores, and each core reading its corresponding partitions using the histograms. So this is how the hybrid join should work. All right, now let me show you the FPGA-based partitioning implementation in detail, and I will walk you through the pipeline, this pipeline, so that the efficiency of this becomes very clear. As you can see here, the partitioning works on cache lines, that is the data width of the QPI, and it is able to accept and produce a cache line at every clock cycle, so no internal locks are necessary. So first let me describe each module here so that this diagram becomes familiar to you. First, we have the hash function module that does hashing and determines which partition a tuple belongs to, and we have, as you can see, we have 8 of them since we are processing 8 tuples in parallel. Second, we have the write combiner modules that the tuples go into after a FIFO. And on the right hand side here, I'm showing you the internal design of one write combiner. And lastly, we have the write back module that reads the tuples in a round robin fashion from the write combiners and writes them back to the main memory. All right, now that we are somewhat familiar, let me actually walk you through how this pipeline works for partitioning data. So when a cache line is received, the tuples first go through the hash function to determine their partitions, and in this example, we are assuming that the hash function is the alphabetical position of a letter. So all the tuples are hashed in parallel, as you can see. In the next cycle, we begin to see the advantage of having a specialized D pipeline on the FPGA. So as you can see here, a new cache line has arrived. And while these tuples go through the hashing, the older tuples that have arrived in the previous cycle will go through the write combining process. So let's see this happening. So as you can see, everything happened in parallel and in the same clock cycle. And this is the advantage of having a pipeline on the FPGA. Now let's focus on the insides of the first write combiner, where a tuple is received. So 3 is the hash and C is the value. So here the current fill rate determines which block RAM the tuple will be written to, and its partition determines the address inside that block RAM. In this case, let's assume all the buffers were empty, and thus the tuple will be written to the first block RAM. And as you can see, the fill rate has been also updated. So we repeat this process. We write the tuples to their corresponding partitions until a full cache line is assembled. And when that happens, we notify the next stage of the pipeline so that these tuples are read from their block RAMs and put into the FIFO. And at the same time, we also reset the few rate that is inside that block RAM. Then the next stage is the write-back circuit reads that cache line from the write combiners. And here on the write-back module, we have two block RAMs to determine the end address. The first one holds the prefix sum for the histogram that can be optionally built in an initial run over the data. I will explain more on that later while discussing the operation modes. And the second block RAM holds the counts of how many cache lines have already been written to the memory to determine the end address. And that's it actually for the core design. So if something is not clear here, I'd be happy to discuss offline and answer your questions in detail. All right, now let me talk about different modes of operation that we have implemented for this design to increase its flexibility and its usefulness for as many applications as possible. The first parameter decides how the output is formatted. First one we have is the so-called hist mode or histogram mode. And in this mode, we actually do an initial pass over the data to build a histogram inside the FPGA. And thus, we save the size of each partition and use that during the second pass to write back the tuples. And the advantage of this approach is that the memory consumption is minimum and it's robust against skew data. The disadvantage is that we perform two passes over the data. Then the second mode is the padding mode, where we assign a fixed size to each partition and we calculate this size according to a formula, number of tuples divided by the fan out plus some padding. And the advantage is that we only have to do one pass over the data. However, if a partition gets filled during the process, we have to abort this and we need to start over. The second parameter decides if we have a row store or a column store. So first, in the first mode, the record ID mode, we assume that the tuples are an X byte key and an Y byte payload. And in this mode, we can read these tuples directly and partition them natively without doing any changes. And in the second mode, the virtual record ID mode, we have an X byte key and the Y byte payload stored separately in memory. So if you want to partition on the keys, for example, we only read the key column, but then we have to append a virtual ID on the FPGA to enable later on materialization. If you don't do that, the reshuffling during the partitioning process would make the materialization impossible. The advantage of having virtual ID mode is we need to read less data in total, and this is good because our implementation is bandwidth bound right now. And disadvantage is the materialization cost, which is, however, not so different than any column store that has to perform materialization. All right, now let me show you the partitioning throughput that we achieve with our implementation compared to related work. These results, all these results are for a fan out of 8,000 and a tuple size of 8 bytes. The first bar is from Polychrono and others in SIGMOD 2014. And the throughput is achieved with a 4-socket machine and 32 cores with all the known optimizations enabled, such as software write combining. The second bar shows the FPGA-based partitioning throughput from Wang and others implemented using OpenCL. Now, the blue bars show the throughput of our FPGA-based implementation. And as we can see, depending on the mode of operation, the throughput changes. So the slowest one is the histogram row ID mode, because the 2 passes over the data have to be performed, and the key column is read. And the fastest one is the padding virtual row ID mode. So the light blue bar shows the partitioning throughput using the 10-core Xeon CPU on the target platform, and we see that the throughput is very similar to the fastest one that the FPGA achieves. However, keep in mind that this is because that the current implementation is bound on the memory bandwidth available in the current platform, which is 6.5 gigabytes per second.
QPI, right?
QPI bandwidth, exactly. So on the right-hand side, I'm showing you the internal processing rate of the circuit for the partitioner. And how we measured this is actually we have implemented a wrapper inside the FPGA that emulates QPI behavior, however with a bandwidth of 25 gigabytes per second. And as we can see, the internal processing throughput is much better, and if we have a platform with 25 gigabytes per second, we will achieve this throughput. We have also made possible to increase the tuple size that the FPGA-based partitioning can handle. It can handle 16, 32, and 64 byte tuples with minimal changes to the architecture. Notice here that as we increase the tuple size, the right combining actually becomes less challenging, and it decreases the complexity of the circuit, which is good because we use less resources on the FPGA. The processing rate remains the same for all these variants. All right, now let me move on to the evaluation. However, before I begin showing you the numbers, I will introduce you the workloads that we have used. We have 4 different key distributions we use for our workloads. The first one is a linear distribution where the keys are unique from 1 to n. These represent just IDs. Then we have randomly distributed keys. And we have some special distribution called reverse and reverse grid, which represents strings and address patterns. And these will show where the hash partitioning becomes better than the radix partitioning. Then we have 5 different workloads. Workloads A and B use both linearly distributed keys, but the build and probe table sizes vary. Then workloads C, D, and E have all equally sized tables, but the key distributions are different, selected from the above table. And these workloads, like I said, will hopefully show you the robustness of hash function used. And the time that we spend on the build and probe will change whether we use a hash partitioning or a radix partitioning. All right. So now let's take a look at the hybrid join performance. So we fixed the partitioning fan out to 8000, which gives the best performance for build and probe. On the x-axis, we have the number of threads that we use to do CPU partitioning and CPU build and probe. And as we can see, the FPGA partitioning in padding row ID mode is faster until 8 threads on the CPU are dedicated to doing partitioning. So we observe that the hybrid processing seems to be performing well. The only artifact that we are observing here is that the build and probe after FPGA partitioning is slightly slower. So we investigated why this happens, and the only reasonable explanation that we came up with is the presence of a cache coherency protocol that is designed for a homogeneous multi-core system. And the same protocol is used here for a heterogeneous multi-socket system, where the FPGA has only 128 kilobytes of last level cache. And since this is the case, and there is no snooping filter on the CPU side, this causes some problems. And more details about this is explained in the paper if you're interested. However, this problem should not occur in the second version of this platform. We performed the same experiment with workload B, where the table sizes are different by an order of magnitude, and the results seem to be very similar to the first experiment. Now I would like to see if hash partitioning versus radix partitioning affects build and probe performance. Here we have workload C, equally sized tables, and randomly distributed keys. On the x-axis we have again the number of threads we use on the CPU. And as we can see, hash partitioning takes longer than radix partitioning on the CPU. On the FPGA, we use only hash partitioning because there is no difference between the two. However, when we look at the build and probe, hash partitioning is not significantly beneficial for this workload. It makes sense because the keys are already randomly distributed here, and even radix partitioning creates uniform partitions. Now let's take a look at workloads D and E, which have again equally sized tables. And now we have this grid and reverse grid distributions. For these distributions, we know that radix partitioning does not achieve uniform partitions. And this shows itself in the build and probe performance. For workload D, it's 11% slower, and for workload E it's 35% slower. Thus, we can see the benefit of using a robust hash function, which the FPGA can do without any performance reduction. All right, let me conclude here. So we have presented a fully pipelined, flexible FPGA-based partitioning that is designed to work on hybrid CPU FPGA platforms. We integrated the FPGA partitioning into a hybrid join where partitioning happens on the FPGA and the build and probe happens on the CPU. And since partitioning is a very important sub-operator, the proposed design should be interesting also for other types of hybrid workloads, not just for joins. We showed that hybrid execution is comparable to a 10-threaded CPU execution despite the limitations of an experimental platform. And this work in that regard should be received as a proof of concept for the potential of future of heterogeneous architectures. So we believe to have shown that FPGA is very efficient at doing robust high fan-out data partitioning. And therefore, in our future work, we plan to use this in a multiple of applications. So the first one that we want to do is we want to implement this partitioning over the network for doing distributed large-scale joins. Then we want to integrate what we have here into an in-memory database, more specifically MongoDB, and have this FPGA partitioning as part of the MongoDB join to accelerate analytical workloads. And we also want to investigate partitioning compressed tuples directly. So imagine if you want to partition a table where the tuples are 5-bit or 3-bit, like these weird bit cases, and you want to partition the table directly, we can do this on the FPGA. However, on the CPU, you have to first decompress and then partition. So this is, again, an interesting case for this work. And that's it. Thank you.
One question?
Shimin Chen from Chinese Academy of Sciences. So how do you deal with virtual to physical address translation in FPGA?
So the FPGA works directly on physical addresses in that case. And how we deal with this is we have a page table on the FPGA side. And the software library allocates a chunk of memory. It can be as large as 16 gigabytes. And then the pages are 4 megabytes large. And each address for that, for each page, the address is written to the FPGA, to the page table, so that the FPGA can directly work on physical addresses.
So I think just one more question here.
Sure. Okay. Probably you could hear me without it, but like, so I mean, the main problem here is like the memory bandwidth, right? So you're memory bound. That's
exactly
what I saw in your results.
Right.
So my question is like, how can the FPGA help you, go beyond that, right? Like, can you use memory, do something, use work in the CPU while the FPGA is partitioning? If the CPU is also memory bound, then what will you do? Like you're still stuck in the CPU, right?
You mean that if the CPU is memory bound?
Yeah, I mean, like if the CPU is memory bound, then you can't do any useful work either case, right? Either you will use your CPU and saturate the bandwidth, or you will use the FPGA and saturate the bandwidth.
Right.
Right. So how can you use the FPGA more creatively there to do something more? That's what I'm saying.
Right. So for the CPU, in order to be bandwidth bound, you need to allocate at least 8 cores. So you have to use most of the CPU resources. That's one thing. The second thing is the FPGA is bandwidth bound in this one, but as I said, the bandwidth of FPGA platforms are also increasing. So we should see large benefit in future platforms where the FPGA bandwidth is larger. And then third of all, we can also imagine this as a hardened macro. So this is as this is a specialized circuit, it can be part of a CPU architecture to do like a specific partitioning operation, and that's why also it's interesting.
Okay, so let's thank the speaker again.